Hi, in this lesson it's time to build some shaders. As you know from lesson 1, Houdini ships with a range of pre-built shaders, but I feel that all Houdini artists should learn how to create them from scratch, so that they understand what's going on under the hood, and also so they can put together lightweight efficient shaders that do one thing well. So right now we're looking at our piece of rubble, which I've cleaned up a little bit so that displacement will work a bit better. We're just looking at it rendering out with the default shader. Probably the simplest shader we can make is a constant shader. So let's make one of those. This is a shader that outputs a color and doesn't do any lighting calculations. Let's start by dropping down a material builder. And we'll call this material builder underscore constant. If we dive inside, we'll see that we have 5 nodes already in here. Let's go through them quickly. So the first two on the left are globals nodes. So these are supplying data from our scene, about our scene, and specifically about the object that the shader is being applied to. And then we have a surface output and a displacement output. So the displacement output is purely outputs data about displacement, so P and N, so position and normal. And the surface output supplies various pieces of information about color, opacity, alpha, normal, and F, which is a BSDF, which is a shading model. And those are being collected by this output collect, which collects various shaders that we wish to attach to our object. We don't need the displacement shaders for this node, so I'm going to delete those. And in fact, we don't need our globals either, so we can get rid of that. So now we just have our surface output and our output collect. I'm going to put down a parameter node, and I'm going to make it a color, and I'm going to call it, let's call it base color. Let's make it cornflower blue, and I'll just plug that into CF, which is our surface color. Now this shade is already connected to this object, and for some reason it's rendering black. In fact, the reason it's rendering black is because we actually need to output something else that is not currently output here. I'm going to drop down a bind export node, and we need to name that CE. CE is color emission. I'll make that also a color, and I'll connect in our cornflower blue. Great, so we've got some blue flat shading happening. Now the one thing you'll notice about this is that not only is our piece of rubble blue, but also we're getting some blue spilling onto the white squares of our checkerboard. And the reason that's happening is because we haven't told it not to literally emit light into the scene, which is very cool, but it's a little bit expensive, and for lots of situations, there's no real reason to do that. In order to stop that from happening, we need to add some properties to our shader. So I'll tab down a properties node, and I'll connect that into the next shading slot of our output connect. And then, as you can see, the properties node is blank by default. If we click on the gear wheel icon, we can edit the parameter interface. In fact, we can edit the rendering parameter specifically. And I've actually already got this search term in here, but if I do it again, I can type emit and hit enter, and it'll narrow the list down to specifically anything with emit in the string. So I can right click to install parameters, or I can drag it in here and then hit accept. And now we have a checkbox that says emission illuminates objects. So if I check that off, we see that we're no longer illuminating the checkerboard, which in most cases is what we're going to want from a constant shader. So one last check to see that everything's looking cool, and we're done with the constant shader. The next shader we're going to build is a basic diffuse shader. So we'll start out by alt dragging on our material builder constant, and that's made a duplicate of that, which we'll call simple diffuse. We'll just jump to our scene view and we'll drag that onto our object, and then go back to the render view. Now if I hit I to dive inside this, obviously we have the same things we had before. So we no longer need our bind, and we don't need our properties. What we do need is a lighting model node. Okay, and we'll connect the base color into the diffuse color for our lighting model, and we'll connect color into the CF, and we'll connect F into F. And as you see, we now have some shading happening. So the F, as I said before, is the BSCF, which is the bidirectional scattering reflectance function, which essentially means that it describes how light bounces off a surface. In Houdini, these are what the manual describes as first-class objects, which means that there's quite a lot you can do with them. So, for example, if I wanted to color this differently, I could just shake loose this base color, and I could put down a multiply node. I can put that in there, and then I can multiply this whole BSDF with a color. Now what that means is that the little bit of specular that you're seeing here is also getting multiplied by the blue color. But it's just interesting to see how this works. We can also disconnect this because the color is contained within the BSDF, so we actually don't need that as well. And then if we want to go to our lighting model, we can see that we have a number of choices to make. We can choose different lighting models. So we can choose Lambertian, which doesn't have any specular. You can see the spec disappearing as it renders. We have Uranier, which looks very similar to Lambert, but it's specially designed for modeling very rough objects. We have Phong model, the famous Phong shader, although it looks kind of metallic because we're tinting the specular with the same color. And then we have Blin. And finally, back to where we started, the Vex specular, which is, I guess, a Houdini-specific shading model, or lighting model, I should say. We can change the colors of the different components, so we can make our spec a bit brighter. In fact, we can make it very bright if we need to. We can overdrive that. And we can change the diffuse color. This, of course, looks black because we're multiplying it by blue, and red multiplied by blue is black. And the ambient color doesn't really do a great deal in any of these lighting models, I don't think. And then we can change the roughness of the specular. But we'll go back to the Lambert. And that's a basic diffuse shader. Now that we've built our simple diffuse shader, I'm going to show you a slightly different way of doing the same thing. So again, we'll duplicate this and we'll just call this diffuse PBR. PBR is physically based rendering, which is how the most used rendering engine in Mantra works. So we'll jump inside again. Oh, and I'm sorry, we should just make sure that this is pointing at the right place. We'll dive inside here and we'll remove our lighting model, and I guess I'll just dump that as well, and we can disconnect this. So we have a range of PBR shaders here. These are all specifically designed to work with the PBR engine. So this is PBR diffuse. It's designed simply to do diffuse shading, so it doesn't contain any specular component. I'm going to plug our base color into the color of the shader, and I'm going to connect up F to F again. And we get something similar to what we saw before. So there aren't many controls on this guy. We have control over diffuse roughness, so we can make the diffuse a little bit kind of flatter. But that's more or less it. In a way, this is even simpler than our simple one, but it will serve as a foundation that we can build up more complex shaders on top of. And finally, again, we see that we're getting some color bouncing onto the white tiles of our checkerboard. Okay, now let's add some reflection. We'll alt-click to drag this one yet again, and we'll call this reflective PBR. And we'll go to the scene view and we'll drag this onto our object again. Jump back to the render view and dive inside. So the next thing we're going to want is a PBR, you guessed it, a PBR reflection. We'll drag over here to make a little bit of space. And what we can do with this is we'll take the base and connect it into the layer output of our PBR diffuse, and then we'll connect the BSDF, the F from PBR reflect, into our surface output. And now, as you can see, we have a shiny object. Now, PBR diffuse and PBR reflect are designed to work properly together. And they produce a very nice shiny result. As we change the index of refraction, we should get different results. And the reason for this is that the IOR controls how the PBR reflect is layered on top of the PBR diffuse. So as we lower the IOR, we tend to only see the reflection at glancing angles. And if we duplicate our palm node, we can make this, say, ref color, and we can connect it into the color of PBR reflect, and we can tint our reflections. If I set the IOR back to 1.5, which is about the IOR of glass, incidentally. Yeah, we see more of those tinted reflections. Okay, and we'll move on to the next shader. Next, let's look at adding some refraction to our shader. Once again, we'll duplicate it and jump to our scene view, drag it on, go back to our render view, and we will call this reflective refractive PBR. We'll dive inside and we'll look at the PBR reflect node again. So although this is called PBR reflect, it's actually a node called PBR non-metallic, and it can handle both reflection and refraction. Let's do that. To turn on refraction, we just have to crank the refract slider up to 1. Right now it's not doing any refraction because we are not shading the back surface. If I turn on shade backside, we should see that we get some refraction as well as the rather nice red reflection we've got there. I'm just going to jump up and set that reflection color to white and jump back. And now if we want to control the mix of our diffuse color and our refraction, the easiest way to do that is to modulate the amount of refraction. So let's do that. Let's drop down a global variables and we'll drop down a unified noise. Then plug our point position into the pause of the noise. And then the noise is outputting a float, so we can plug that into refract. Set the frequency to say 4 by 4 by 4, and another 4 for good measure, and we'll see what that does. Cool. We're starting to get a mix between our blue PBR diffuse and our refractive material. In order to make that a little bit more apparent, I'm going to create a ramp parameter and just drop that onto the wire from unified noise to PBR reflect. This should be a spline ramp. We'll jump up to the interface and we'll set up that ramp so that we get a slightly starker change in shader. And we'll tidy things up a little bit while that's rendering. And there we've got something pretty cool. We've got reflection, we've got refraction, and we have a diffuse color all working together in harmony. Now let's look at displacement. I'm going to duplicate our diffuse material this time. And we'll call that diffuse PBR displaced. and we see that it's our nice smooth diffuse surface. We'll jump inside, and this is nice and simple. So to add a displacement, there's not a huge amount we need to do. The first thing we're going to need is a displace node. Then we will need a output variables and parameters node. This defaults to surface, and we're going to set that to displacement, and we'll connect that into the next slot of our output collect. Then we just put out p into p and out n into n. You can see something interesting is happening here already. For good measure, let's create a global variables node, and we'll connect p into p and n into n. This isn't strictly necessary. Displace is smart enough to read those attributes off the mesh being rendered, but it's good to do that. Sometimes we might want to manipulate these on their journey between our globals node and our displace node. We'll take the displace effect down a little bit. Right now, this is just pushing it a global amount of 0.258 units along the normal. It's looking kind of messy. There are a couple more things we need to do. The first thing we want to do is add a pattern to displace it by. So we'll create a noise. Let's go for the unified noise again. We'll plug P into pos on the unified noise, and then we'll take the noise and we'll plug it into our value. Let's make that 3 by 3 by 3 by 3. And we can increase this a little bit. And then the most important thing that we have to do to stop this from breaking if we push it any further is to add another properties node. There it is. Again, we'll plug that into our output collect. And then under properties, we want to hit the gear icon, and under rendering properties, this time we're looking for band, and we're looking for displacement band. So I'll right click install parameters to install that, and then hit accept. It's very important that we set this, otherwise it's possible to have our displacement kind of breaking as the displacement gets pushed out and it gets clipped against the bounding box of the original object. So Mantra needs to know how far the bounding box should be expanded to incorporate the displacement. So we'll make that 0.3, say. The actual value of this should be the same or maybe slightly higher than the maximum amount that you anticipate your object being displaced. And in fact, if you look at the principal shader, there's quite a lot of work that goes on inside that shader to determine a value for a displacement bound. Okay, that's how you make a displacement shader. We can make this more interesting by turning that into a fractal. And then we can do things like have a vector displacement. Right now, this is just outputting a single value, but we can make that 3D noise going out. And it's probably way too big. Oh, it's in tangent space, so let's set that to world space. There we go. And something else to note about displacement is that on your object, so in this case it's render rubble chunk 1, you need to look out for the amount for the dicing. So if you're finding that this is getting kind of broken, you can increase the shading quality, which will dice the geometry more finely. It's also sometimes worth looking at render polygons as subdivisions. This will take a little bit longer because it has to subdivide the geometry before rendering, which for a large mesh can take a little while, but it will provide higher quality and usually better quality, especially with displacements. Okay, and I think that's probably as much as I want to say at this point about displacements. The last type of shader I want to cover in this lesson is a volume shader, which obviously is fairly important for effects work. So I'm going to stop that render. We're going to jump up, and going inside here, I have a VDB from polygons node, which I'm just going to enable. And now if we go to our scene view, we have a slightly broken due to my graphics card representation of a volume. And then if we go back to the MatNet, I'm going to drop down a fresh material builder. And we'll call this one material builder underscore volume, as you might have guessed. Let's drag it onto our object. Go to render view, and if we hit render, we should see very little. So the first thing we're going to need for this is a compute lighting. And we'll connect the out F into F. And we'll just hook these up too as well, because we need to set the opacity. Next up, we need a node called PBR volume phase function. That goes into F. We connect the BSCF into F. Now, interestingly, we're now getting a volume render, but what we're actually seeing is the entire VDB filled with a very dense volume. It's almost as though we don't have any opacity, and that's actually what's happening. So then we need a node called volume density to opacity, so we'll drop one of those down. And we need to multiply the opacity going into our compute lighting by this density to opacity node. So we'll take this and we'll make this, we'll convert this to a vector using a float to vector node. We'll connect that up to OF. Then we'll take our surface globals and we'll just switch this to output a single variable. And the one we want is change in position with depth. And we need to plug that into our distance. And finally, I believe we will need a bind. So bind fetches a value from the geometry. So the value we need from our geometry is density, which is the name of the only volume that we have in our scene. And if we give that a minute to cook, we should get something more like a normal volume. Now right now our density is fairly low, so I'm going to add a parameter that will enable us to scale the density. So there it is. We'll call this density scale. It's a float and that's fine, and we will drop down and multiply. And now if we go up to the top of our shader, we can multiply this by, say, 10. And see what that does for us. Okay, that's looking a little bit more like a bit more like the sort of volume that we would expect to see. Now let's modulate the density of our volume with the noise function. We'll drop down another unified noise and a globals. As before, we'll connect the P into the pause of the unified noise, and then because this unified noise is set to output 1D noise and we have floats here, we can just multiply that directly. And then we can change the frequency of this. So let's go 5 by 5 by 5. And we'll see what that does. I think I'll add another ramp. Ramps are great for manipulating values like this. Again, this should be a spline ramp. And we'll do something similar to what we did before. We'll just increase the contrast of our noise a little bit. Or quite a lot, in fact. And as you can see, we're starting to cut some really nice holes into our volume. And if we want to increase the detail a little bit, we can switch our unified noise to use a fractal. And now we should get something a little more detailed. There it is. So this is a lot of the kind of stuff that people do with VOPs with VOPnets in SOPs. But obviously you can do exactly the same thing at render time in the shader, and potentially this is quicker. Because you don't need to have a very detailed voxel count, a very high voxel count in SOPs in order to do this. You can do this on a completely continuous volume. And it's only, the detail is only determined by the rate at which you're ray marching the volume in the renderer, and that's controllable at render time. Okay, and that's it for our basic volume shader. The last shader that I want to put together in this lesson is a volume shader that has displacement. So I'm going to duplicate our material builder volume and put it there, and I will call it material builder volume disp. We'll drag it onto our volume and jump back to the render view. In order to displace a volume, we're going to need exactly the same displacement node as we use for our surface. So I'm going to drop that down. We'll also need an output variables node. So we'll put that down. We'll plug this into our output collect, and we'll plug just the P from our displaced node into, I'm sorry, we just need to change the context for that. We'll plug just the P into the P of our output node. And then for displacement, we're not displacing along the normal. We're going to do a vector displacement. And rather than tangent space, we're going to do this in world space. Then I'm going to take the set of nodes we had over here. I'm going to disconnect this ramp from our density scale. So now we should just get a homogeneous volume here. And I'm going to plug, not the ramp, but the 3D output of this noise into our value. Then lastly, I'll plug P from our globals into displace. And there we have volume displacement. It's surprisingly easy. And obviously this is used to great effect in the Pyro shader, but it's good to have an understanding of how this works at the nuts and bolts level. I'll just render a little bit along the edge so that you can see that it's actually breaking the profile. And clearly this has a lot of power for adding detail to clouds, smoke, and anything else that's kind of fluffy and gaseous. And that's it for displace volume, and that's also it for the shaders lesson. I hope that this has given you a good introduction to constructing shaders in Houdini. I'll see you in the next lesson.